Mm, Okay, we're going to be working some textbook problems today just to kind of pull together everything that we've done so far. So I'm just getting these ready. If you have a textbook, you may want to get that out because I'm not sure how clear you guys will be able to see the problems. Which one did I just do? 51. And so we'll be on pages 267 and 268. And out of the ones that I assigned today, I tried to do um, do one of each type, and then there'll just be um, a couple that you should be able to do on your own, which hopefully some of these you'll be able to. I'll kind of take it slow so you can work along with me. Um, and there's an assessment in Otis for you to attach your work for today too. But hopefully this will help with the quest problems, and also if there's any questions you have about what we've been doing, it will bring those up. One more to do here. Let's see. 54. And let's go. Okay. All right, let's go ahead and get started. So the first one, it's on page 267, number 36. Okay. Skylar. Okay. All right. Okay, so here we've got our reaction, and it says how much heat is evolved for the production of 1 mole of the liquid water. Okay, so this one is actually fairly straightforward in that. So this, we have our ratio there, and I'll just, so 2 moles of water is 572 kilojoules, which I know you guys can do this math in your head, but 1 water then is going to be what we're solving for. So it's just going to be half of 572. So 286 kilojoules. All right. And then how much heat is evolved when 4.03 grams of hydrogen, remember hydrogen is H2. All right. So if I do 4.53 divided by 2 hydrogens. All right. So that's, I'm getting 2.25 moles. All right. So from the equation, 2 hydrogens are 572 kilojoules. So 2.25 hydrogens. We're solving for that. And so I have 572 times 2.25 and divided by 2. So I get 643.5 kilojoules. right? How much heat is evolved when 186 grams of oxygen is reacted? So let's see, 186 divided by 2. So I get 5.82 moles there. So for every one oxygen, I get 572 kilojoules. And here I have 5.82. And so we get times 5.82. So I'm getting 3329 kilojoules. All right, and the last one of these, D. Okay, total volume of hydrogen gas to fill the Hindenburg. So I have a volume of 2 times 10 to the 8th liters. Pressure is 1 atm. My temperature is 25 plus 273, so 298. And so let's see, PV equals nRT. That gives me 1 the 8th and 1 and 298. So that gives us E8 divided by, so I get a really big number. All right, so this is, we're doing hydrogen. All right, which is 2. So 2 hydrogens is 572 kilojoules. And this is, what is that? 8,174,676 moles of hydrogen. All right, so that's going to be a big number. It's 572 and divided by 2. All right, let's just do this in 2.3 times 10 to the 10 to the 9th kilojoules. Okay, so that one was pretty straightforward. Okay, so the next one is, let's look at number 38. Okay. All right. And we want the enthalpy change for each of the following cases. Okay, so this one is actually kind of similar to the other one. I have 1 gram of methane. So methane is 1 carbon and 4 hydrogens. Okay, so 1 divided by 16. So this one is 0.0625 methanes of that, and this is 1 methane to 891 kilojoules. So that would be times 891. All right, or 55.7 kilojoules. So that's part A. And then part B, let's see, so PV equals nRT. I have 740 torr. So divide by 760, that is 0.97 atmospheres, 1,000 liters in, and 298 Kelvin. Divide by, so I'm getting 39.6. And this is, oh, still methane gas. So 1 CH4 over 891 equals 39.6 over unknown. So that times 891, 35326 kilojoules. Okay, all right, so we should be good to go on ones like that. All right, let's do, this is 42. All right, so here, calculate the energy required to raise the temperature of 150 grams of silver. All right, and so it gives our specific heat of silver from 273 Kelvin to 298. So we're wanting, so Q Cm delta T. And so 0.24, and I have 150 grams, and T final is 298, T initial is 273. All right, 298 minus 273 times 150 times 0.24. Okay, so I'm getting 900, and that's going to be joules there. Okay. All right. And so I think B and C are very similar. So I'm going to leave B and C for you guys to do, unless anybody has a question on that. Those are, it's pretty similar to A on that.
Ma'am, before you go
Uh-huh.
to the next slide, can you go
Yeah.
back to the last one for a few seconds?
Yeah.
Oh, okay. Okay, thank you. Sorry.
Sure. All right. Okay, 46. Let's see what this one is. Biology experiment requires prep of a water bath at 37 degrees Celsius. The temperature, the cold water is 22 and the hot is 55. If I start with 90 grams of cold water, what mass of hot water? Okay, so this is really kind of like the metal in the water one. We're going to treat it that way anyway. All right, so we're going to say that minus Q of the hot water is going to equal Q of the cold. All right, and so let's just, we'll make our little table here. All right, and so we have mass, and they both have the same specific heat. So T initial, T final. Okay, so that's what we're solving for, is the mass of the hot water, 90 of the cold. Let's see, the cold tap water is going to be 22. The hot is going to be 55. Our final is going to be the same for both, which is, we want it to be 37. Okay, so we want to know how much hot we need there. So, all right, so minus, oops, let's do this in the right order. Okay, so 4.18 times the mass, and the hot is going to be 37 minus 55. That's going to equal 4.18 times 90, and then 37 minus 22. All right, 4.18 times 90 times 37 2. Okay, 5, 6, 4, 3. And then 37 minus 55 times 4.18. So mass times 75.24. And so I'm getting a mass of 75 grams that we would need for that one. Okay. All right.
Mr. Billy,
Yes.
for that one, I just worked it without the 4.18 since it's the same.
Oh,
like,
sure. Yeah.
each other out, and you got the same thing.
Yes.
You
yes.
just you don't get the negative, so you get a negative instead of positive. But or at least I did.
You would get a positive if you did for the like change in temperature on the other side. If you did 50 on the left side, if you did 55 minus 37 instead of
That's
37 minus
negative.
35, yeah,
You
then
get
you would
like
get
a negative 18x.
Oh, well, maybe I'm just wrong.
Well, yeah. The 4.18 will cancel, but then you've got this negative on this side here.
Oh, you leave that, okay.
Yeah, and that's
Yeah.
that'll give you a negative. So that's what.
Yeah, I would have left that and just done the actual numbers. I would have.
Okay. All right. Let's see. All right, 51. Okay, so here's one where we are. Okay, so we are reacting these two solutions, and so we want it in kilojoules per mole of silver chloride form, and so and this one is telling us to use a solution mass of 100 grams on there, and that the solution has the same specific heat as water. Okay, so let's look at what we've got here. All right, so this is just giving us our net ionic equation to use. So there's the silver and the chloride gives me silver chloride. And so I have 0.05 of 0.1 molar. And the same thing over here, 0.05 of 0.1 molar. So they're going to be both will be completely consumed because it's 1 to 1, 0.05. All right, so I have 0.005 of this, 0.005 of that. They're both going to 0. That one starts at 0. And then that's plus 0.005. And it wants it per mole of that formed. Okay, so we'll do our Q Cm delta T and 4.18 of a mass of 100 and final temperature 23.4 and oops, what am I doing? Then the initial was 22.6. So that gives me okay, so I'm getting 334.4, and that's going to be joules, all right, which will be 0.3344 kilojoules. All right, so oh wait, what is it asking for? The heat that accompanies this reaction. Okay, yeah, so we're going to do this. So it's the heat of that or reaction process there. Q per mole. So 0.3344 kilojoules, and it was per mole of the precipitate. Okay, so 0.3344 divided by 0.005. So I'm getting 66.9 kilojoules per, whoops, I dropped my negative, didn't I? Don't want to do that.
So
Okay.
if the in the BCA table, if the like moles have been different, which mole would you use for that, like that last part in green?
Here in the problem, it said that it wanted it per mole of the AgCl formed. So even if it was a limiting reactant, I still would have looked to see how many moles of the precipitate was formed.
Thanks.
Uh-huh. Okay. All right. Okay, here's another one with a reaction. All right, so we want the heat when, let me rewrite this down so I can do a BCA, 2HCl plus BaOH2, BaCl2, and 2H2O. And it's saying that delta H minus 118 kilojoules. Oops, well, come back here. All right, and so I have 0.1 liters of 0.5 molar and 0.3 liters of 0.1 molarity. So all right, so 0.05, 0.03, okay, and we're just wanting the heat form. So essentially, we're just looking to see what the change is, and then we'll just use that. So let's see, 0.03 times 2 is 0.06. So the HCl is going to be my limiting to 0. All right, and it wants just the heat generated. So let's see. Oh, it wants the final temperature. Okay, so I'm going to use this to get my Q. All right, so that means, all right, so 2 moles of HCl gives me 118 kilojoules, and I have 0.05 moles. Okay, so that's going to be 0.05 times 118 divided by 2. So I'm getting 2.95 kilojoules, which is going to be 2950 joules. So that's my Q. All right, and then let me go back up and find my, what did we have? Transfer this down here. So I have my mass is 400, it says. T initial is 25. And we're going to use 4.18 for our specific heat on there. Okay, so Q is Cm delta T. So 2950 joules is equal to 4.18 times 400. And then I'm solving for T final. My T initial was 25. Okay, 4.18 times 400. So I get 1672 TF minus 41800. Okay, and then that plus so 750 1672 T final, and then so divide by, so I'm getting a T final of 26.8. Okay, which makes sense because the delta H was negative, so that's heat that's being generated. So we would expect our temperature to go up, the temperature of the water to go up on there. Okay, so kind of summarizing that one then, right? We did our BCA because we needed to know how many moles were going to reacted. And so I used the change, right, in my ratio with the coefficient and the delta H to get my Q, and then use that with the given information, the mass and initial temperature, to find T final on there. Okay, the other problems, I have them in Otis, but let me just flip to that page because I have them marked in here. Okay, so the ones we did not do right now that I want you to do on your own. So on page 267, we still have number 35. And you can check your answers in the back of the book on these odd ones. Page 268, I had 44 and 45, and let's see, I'll add the answer to the even one. I'll add that to the class board, to the today's post on the class board, and then 53. Okay. So those are the remaining ones to work out. And I think we worked one kind of like each of those on there already today. Okay, I haven't looked at the Jamboard to see, but let me check it while we're here, see if anything was on there. Let's see. Part 2 of the, oh, okay. All right, so here we're finding the heat that's generated by burning the coal. All right, and so then in part 2, all right, it's water. So, all right, water. So my C would be 4.18, right? And you're going to do, we're burning something and it wants the mass to heat it. All right. So the Q, my Q is the Q that's from part 1, but in joules. And the C is 4.18. So then you would just do your Q is MC delta T on there. And then you'd just be solving for your mass because we have our T final and T initial, all that for that one. Okay. Let's see. Okay. Wants it in calories. All right. So all right. So first off, C2H2 plus oxygen. We're going to get CO2 and H2O. Okay, so balanced, that's a 2, and let's see. All right, so for this one, let's see, I get 4, 5, so that would be like a 2.5 on that one. So remember, for the heat of combustion, you want to balance it so that there's a 1 on the thing that's being burned. All right, and because that's what the delta H that they're giving me here. Right, so I have 2.7 grams, and the delta H is 310.61 kilocalories per mole. Okay, so yeah, so that delta H that they're giving us, because it's a heat of combustion, goes with this equation balanced that way. No, does that matter on this one? Let me see. So, okay, so 1 mole of C2H2 is 310.61 kilocalories. So, all right, and 2.7, so 2, just double check everything. All right, so that molar mass they used is right, so that's going to give me all right, so 0.10373 moles. All right, 0.10373 moles. And then we'd be solving for and that's going to give me kilocalories, right? And then times 1,000, because it wants it in calories. On there. So let me just 0.10373. Yeah, I'm not sure what the excuse me. Okay, but that should get you the right answer on that one. All right, so we have okay, so we're making water. So that's a 2 and a 2. All right, and that plus what's written like that's in saying that delta H, because the energy's on our product side, it's negative because it's giving off energy. So minus 286, which I don't think it necessarily matters for this problem, but all right, so here we want, okay, so here it's giving us So our Q is 260,000 kilocalories. All right, and then we need it in kilojoules because that's what our delta H is in. So if 1 calorie is that many joules, then 1 kilocalorie is going to be no, wait, go the other way. No, that's right. 4184. No, that's not right. Goes the other way. Let me just do it this way. All right. All right, 1 kilocalorie is 1,000 calories. 1 calorie is 4.184 joules. Oops. Okay, that's why, because that 1,000 will cancel out. All right, so anyway, yeah, okay. 1 kilojoule. Yeah, that's going to cancel. So 260,000 times 4.184. Okay, so that gives me 1087840 kilojoules. Okay, and so then I have to move my ratio, run out of room. All right, so then up here, I want oxygen. So 1 oxygen gives me 286 kilojoules. And I want to know how many moles of oxygen will give me this many, 7840 kilojoules. All right, and then so once I get that, it wants it in, oh, I don't know if it wanted moles or grams, but so check the problem to see if it wanted moles or grams on that. Oops. Oh, not writing. Okay, let's see. Okay, so we have NBr3 plus 3H2O is 3HOBr plus NH3, and it's saying that delta H is a positive 81 kilojoules. And it says, what is the expected energy change for the reverse reaction? Okay, all right, so if I reverse it, if it's endothermic going forward, if I reverse it, it's going to be exothermic. So delta H for the reverse is negative 81. So that's why this is going to be negative. And then let's see then. So 9 moles and 2 moles. All right, so let me rewrite it here. Let's change colors. So 3HOBr plus NH3 yields NBr3 plus 3H2O. All right, and it's saying I have 9 moles of this and 2 moles of that. Okay. All right, so the ammonia is going to be the limiting. So -2. All right, so if I have, my equation says that 1 mole of NH3 releases 81, minus 81 kilojoules. And then I have 2 moles of NH3. And so, yeah, so it's times 2. So that's why you get minus 162 for that one on there. Okay. Any other questions? Any other questions that we need to address? Let me get back to where I can see.
There's one on. It's on the KMT quest.
Okay. Let me pull that up.
And it's like it's not like a problem that you have to work out.
Mhm.
I just don't know the answer. It's
Okay.
for me, it's number 3. It's which of the following statements are not consistent with the KMT? And I mean, there's like a lot of options. I can put it on the Jamboard real fast if you want.
Okay. Yeah, that'd be good.
Okay, sorry. This is
Oh, that's all right.
Oh man. Okay. It's on slide 20 now, but there's stuff
On
that isn't part of the problem.
Wait, are you on the new Jamboard?
Oh, I may not be. Oh no, I don't think I am.
Okay, hang on. I can go back to the other one. Hang on. Let me just get back to where I was before. Okay, let me pull up the other Jamboard.
Sorry, this is unit 5, I think.
Okay, all right. Let's see. Uh, all right, and you said page 20?
Yes, ma'am.
Okay. Okay. Let's see. Which one is that? All right. Okay, so all right, so kinetic molecular theory, we said that the our volume of the molecules is negligible. It says that that the Kelvin temperature is proportional to the kinetic energy. It said that the attractive forces are also negligible, and that the pressure comes from the collisions with the container walls. Okay. All right, so let's look at these in terms of that, and we want to know which one is not consistent. Okay. Oh, and that's the other thing. All right. Also, So it deviates at low temperatures or high pressures, which corresponds to a small volume. All right, so the volume occupied by the molecules of a gas becomes significant only at a very low pressure. And that one isn't consistent because it's at high pressures. At low pressures, you have a really large volume. So the volume of the molecules would not be significant if at a large at a low pressure, which would be a large volume. Okay. And then to look at the others. The attractive forces become significant only at low temperatures. That is true. All right. Collisions between the molecules of a gas are elastic. Okay, what that means there is that if they collide with each other, they don't lose any energy, which is true if we are saying attractive forces are negligible. If the attractive forces come into play, then they lose some energy and the collisions are not considered elastic. But that's what that term there means. Let's see, except near the liquefaction point, attractive forces between molecules of a gas are very small. Yes, that's what we're assuming in kinetic molecular theory. And a given sample of gas is mostly empty space, and that this is like meaning if it's close to the temperature where it's going to condense, which would be considered a low temperature on there. Does that make sense?
Yes, ma'am. Thank you.
Mm-hmm.
So on number 4 of that one, near the liquefaction point, is because the volume's getting smaller that the attractive forces start happening.
It's the liquefaction point, right? That means we've lowered the temperature to the point where it's almost ready to condense. And so the liquefaction point is going to be associated with as a low temperature for that
So the
gas.
molecules are moving slower.
Yes, yes.
Ms. DeVilly,
Mhm.
on Otis, the
Yeah.
Unit 4 test isn't marked as graded, it's marked as turned in. So could you like mark it as turned in so that we can like look at them? Does that make sense? Like so we can look at it like
Oh, okay. Hang on. Well, and let's see. Actually, I need to, because what I did, yeah, let me see if I can return them to you in because it makes me like I have to pull them out and grade them, but I have them all, like I have all of the marked up tests. So let me let me put that on my to-do list to get those
thank you.
back up there. Uh-huh. Okay. Anything else for today?
I have a question. It's not about the quest, but it's on number 53 for the textbook. I'm assuming you work it out like number 54, but I don't know what amount of grams you'd use.
Okay. Okay, for this one, since it's dissolving, you would add the 11 grams of the solute to the 125 grams of water.
Okay,
To-
and
and-
then when you use your Q equals,
Uh-huh.
you use that for
Mhm.
your grams.
Yes, in your Q equation, use that for the grams, and then you'll just use the 11 grams of the calcium chloride you'll use the moles of calcium chloride
Yeah.
with that delta H. Yeah.
Okay.
Yes.
Thank you.
Mm-hmm.
Mr. Billy, I actually do have a question about one of the quest questions. Can I post it on the part 2 board?
Oh, okay. Let me move this one. Okay. What page were we on? Are you going to put it on 10? Page 10?
Yes.
Okay.
Give me 1 second.
Mm-hmm. Oh, okay. All right. So here we have nitrogen versus some other gas. All right. And so the rate of the other gas. All right. It's going to equal, so we'll have the square root of the mass of the nitrogen on the bottom, the square root, the mass of the other gas on the top. So we would have 1.7 times as fast. So we would have 1.7 to 1 here. And then what is that going to be? 2 nitrogens is going to be 28.014. And then the square root of the molar mass of the gas would be there. And then you would just solve for that molar mass.
Okay, and just so I'm following, we put the rate of the nitrogen on top because it's 1.7 times faster.
Yes.
And then but then we have to take the inverse in order to put it into our square root function. Okay.
Yes. As long as the rate of the nitrogen is across from the square root of its molar mass. Yeah.
Okay. And then down there on the problem, we would multiply by the square root of 28.014 and then square that number in order
Yes.
to get our solution. Okay. Thank you.
Anything else?
I don't think so.
Okay. Well, I will see you guys tomorrow. Have a good day.
One question for just you for APCSP.
Yeah.
I just wanted to know if you've done mine yet, so I know to look for it. Do you think you've done the practice?
I don't think I've done yours yet. I've got a faculty meeting at 9:30, but I
I'm not
will.
trying to rush. I just.
Oh no, that's
where
not.
do you
That's
think
not a
it's
problem.
where are you gonna like? Where should I find it?
Oh, email. I'll email it to you.
Okay. Thank you.
Sure.
Bye.
Bye.